For over a century, we've been promised flying cars. But what if I told you that the future of urban travel isn't about cars at all? It's about fundamentally rethinking how aircraft work. Right now, hundreds of companies are racing to certify a new generation of aircraft that could transform how we move both people and cargo. But there's a fascinating engineering debate happening. Should we have these aircraft take off vertically, like helicopters, or is shortening the runway enough? I'm Eric Hillsberg, and today we're diving into the technology, engineering trade offs, and real world applications of the resurgent electric aviation market. eVTOL versus eSTOL, and how the why now moment for electric flight involves much more complex engineering considerations than you might expect. But first, a quick disclaimer. I'm the aerospace product manager at MathWorks, the makers of MATLAB and Simulink, and a software supplier for many aerospace companies. But all the views that I'm sharing today are entirely my own. Alright, let's get some basics out of the way. eVTOL stands for Electric Vertical Takeoff and Landing. Think of them as the electric evolution of helicopters. They can take off and land vertically, but instead of burning jet fuel, they're powered entirely by electric motors and batteries. Now, if you've ever looked inside of a helicopter, you'll see why engineers are excited about going electric. Traditional helicopters are mechanical marvels, but they're incredibly complex. You've got a main rotor, tail rotor, splash plates, collective and cyclic controls, complex transmissions, gearboxes, hydraulics. It's a symphony of moving parts that requires constant maintenance. eVTOLs eliminate most of this complexity. Instead of one or two rotors, they typically use multiple small electric motors distributed around the aircraft. This is called distributed electric propulsion, or DEP, and it represents a fundamental shift in aircraft design technology and philosophy. But here's where it gets interesting. There's no right way to build an eVTOL. Some look like giant drones with multiple rotors that only point upwards. Some have wings with rotors that tilt from vertical to horizontal. Some use separate sets of rotors for lifting and forward flight. We're still in the experimental phase, with each company betting on different approaches. Companies like Joby Aviation are developing tilt rotor designs that transition from helicopter-like hover to airplane-like forward flight. Archer Aviation's Midnight uses a lift plus cruise configuration with a mix of dedicated hover rotors and tilt rotors. Volocopter takes a multi-copter approach with 18 fixed rotors arranged around their circular frame. Lilium has developed ducted fans integrated into the wings and canard surfaces. Each approach involves fundamental engineering trade-offs: complexity, efficiency, safety, performance, and that's before we even get to the question of whether they should take off vertically at all. So why is this happening now? The concept of electric vertical flight isn't new. People have been building electric helicopters for decades. But the advancements of several critical technologies are what's enabling this transition. First, and most obviously, batteries. Electric cars are everywhere now, and this is because lithium-ion energy density has roughly tripled since the early 2000s, while costs have dropped by over 90%. But for eVTOL, it's not just about energy density. Modern batteries can deliver high-powered requirements for vertical flight while maintaining safety margins that aviation demands. A typical eVTOL might need 400 to 600 kilowatts of power for takeoff and hover. That's enough to power several homes. The same aircraft might need only 100 to 150 kilowatts for efficient cruise flight. This power variation is exactly what modern battery technology was made for. Second, electric motors have achieved aviation-grade power-to-weight ratios. Modern permanent magnet synchronous motors can achieve 5 to 10 kilowatts per kilogram, competitive with small turbine engines, but with far fewer moving parts and much lower maintenance requirements. But the real breakthrough is distributed electric propulsion. Instead of mechanically distributing power through gearboxes and shafts, you distribute it electrically. Each motor can be independently controlled with millisecond precision. If one motor fails, the others can compensate, something impossible with mechanical systems. Third, computational tools have revolutionized aircraft design. High-fidelity computational fluid dynamics, or CFD, means you can test thousands of design iterations virtually before building anything physical. Companies are also able to use AI and machine learning to optimize everything from rotor blade shape to flight control algorithms. Critically, many eVTOL designs are inherently unstable due to their multi-rotor configurations. They require sophisticated fly-by-wire flight control computers to maintain stable flight. These systems make rapid, precise adjustments hundreds of times per second that would be impossible for human pilots to execute manually. While fly-by-wire technology isn't new, the technology has benefited from advances in high-performance, lightweight computing hardware that enables real-time control of previously unflyable aircraft configurations. Fourth, advanced manufacturing. Carbon fiber composites offer strength-to-weight ratios impossible with traditional materials. Additive manufacturing allows complex, lightweight geometries that can't be machined or molded. Companies like Beta Technologies are using these techniques to build aircraft structures that are both lighter and stronger than conventional designs. Finally, there's growing pressure for sustainable urban mobility solutions. Cities are increasingly congested, and there's mounting pressure to reduce transportation emissions. eVTOLs promise zero local emissions and the ability to bypass ground infrastructure entirely. The result? Billions in investment, hundreds of aircraft concepts worldwide, and projected markets that could reach tens of billions by 2030. But here's the critical question. Can the technology actually deliver on those promises? The vision is compelling. Imagine summoning an air taxi from your smartphone, taking off from a rooftop vertiport, and flying directly to your destination while bypassing traffic entirely. No more sitting in gridlock, just point-to-point transportation at 150 miles per hour. But as always, the engineering reality is more complex. Let's talk about the fundamental physics problem, the disk loading equation. The power required for vertical flight is inversely related to the area swept by your rotors. Smaller rotors require exponentially more power to generate the same lift. A traditional helicopter might have a disk loading of 5 to 10 pounds per square foot of rotor area. Many eVTOL designs have disk loadings of 15 to 75 pounds per square foot or higher. This means they're inherently less efficient in hover, exactly when they need their maximum efficiency. Then there's the energy density constraint. Jet fuel contains 43 megajoules per kilogram. The best lithium-ion batteries manage less than 1 megajoule per kilogram, at best, 60 to 1 disadvantage. Even accounting for the higher electric motor efficiency, this creates fundamental range and payload limitations. Most eVTOL designs are targeting 25 to 150 mile ranges, with 4 to 5 passengers including a pilot. Compare that to a traditional helicopter like the Bell 206, which can carry similar passenger loads but for 250 to 400 miles depending on the variant. The physics haven't changed. You're trading range and payload for zero emissions and potentially lower operating costs. There's also the hope that battery technology continues to improve at a rapid pace to lengthen the range. Then there's the infrastructure. eVTOLs need vertiports, specialized landing facilities with charging infrastructure, weather protection, and passenger amenities. Unlike airports, these need to be distributed throughout urban areas, close to where people actually want to go. Rooftops could potentially be retrofit for this purpose, but this would be extremely expensive. There's also the noise question. While eVTOLs benefit from distributed electric propulsion, they're not silent. The acoustic signature is different from helicopters, less of a distinctive chop-chop of blade slap, but significant noise during takeoff and landing operations. Finally, there's certification. The FAA has never certified an aircraft like this before. They're literally writing the rulebook as companies submit the designs. Initial hopes for commercial operations have moved from the mid-2020s to the latter part of the decade, as regulatory frameworks still develop. Each configuration requires different approaches to safety analysis. How do you prove that a 12-rotor aircraft is safe when losing multiple rotors? What training do pilots need for aircraft that can transition from helicopter to airplane flight modes? These aren't just technical questions, they're regulatory ones that require entirely new frameworks. Now, what if there's a more traditional approach that addresses some of these challenges through different engineering trade-offs? Enter eSTOL, electric short takeoff and landing. These are much more similar to the aircraft of today. Instead of taking off vertically, they use very short runways, sometimes as little as 150 feet. The key technology is called blown lift. Electric propellers blow high-velocity air over large wing flaps, dramatically increasing lift at low speeds. Companies like Electra can achieve takeoff speeds of just 35 miles per hour and minimum flight speeds of 25 miles per hour, slow enough to operate from incredibly short runways. Here's a crucial difference. Short takeoff requires significantly less energy than vertical takeoff. While an eVTOL might need 500 kilowatts for vertical lift, an eSTOL might need only 200 kilowatts for takeoff. This translates directly into longer range, higher payloads, and smaller batteries. Electra's prototype is designed for 1,100 plus nautical miles with up to 9 passengers. Substantially different performance characteristics than most eVTOL designs. The trade-off: you do need a runway, even if it's a very short one. But here's where it gets interesting from an infrastructure perspective. The United States has over 5,000 existing regional airports, most of them underutilized. Many of these already have runways longer than 300 feet, and they just need charging infrastructure, not complete reconstruction. Compare this to eVTOLs, which need entirely new vertiports in urban areas. Real estate in city centers is expensive and politically complex. Getting zoning approval for a new aviation facility in Manhattan presents entirely different challenges than adding charging stations to an existing airport in New Jersey. From a certification standpoint, eSTOLs are closer to conventional aircraft and should therefore be easier to certify. Companies like Electra are working within established frameworks rather than creating entirely new ones. The blown lift technology is complex, but it's an evolution of existing concepts rather than a revolution. However, all electric aircraft face similar challenges in demonstrating safety and reliability of their batteries. eSTOLs are positioning themselves differently than eVTOLs. Instead of urban air taxis competing with ground transportation, they're targeting regional routes that currently have poor connectivity. For example, connecting smaller cities that airlines have abandoned, or providing service to destinations with geographic barriers. Data from companies like Connect Air suggests strong demand for this model. Significant percentages of customers want to bypass major airport hubs, and average flight distances fit well within the eSTOL capabilities. This market positioning benefits from a key technical advantage: noise characteristics. The distributed electric propulsion offers the same acoustic benefits as the eVTOL. This noise reduction is particularly valuable at regional airports, which are often located closer to residential communities than major commercial hubs. Unlike urban vertiports that need extensive community approval processes, many regional airports already have operational approval and would benefit from quieter aircraft that maintain good neighbor relationships. The improved acoustic signature helps regional operators expand service hours and frequency without triggering additional noise restrictions. An important note here is that many eSTOL designs use hybrid electric propulsion, batteries for quiet takeoff and landing, with a small turbo generator for cruise flight. This addresses the energy density limitations of pure battery systems while maintaining environmental benefits for airport communities. While some eVTOL companies are exploring hybrid electric systems, the leading eVTOL developers are primarily focused on their pure electric designs. Electra claim that their hybrid systems can reduce fuel consumption by 40% compared to conventional aircraft, while eliminating the need for ground charging infrastructure by recharging the batteries in the air. To understand some of the biggest promises of eVTOLs, it's worth examining the military's experience with the V-22 Osprey, the world's most successful production tilt-rotor aircraft. Since its introduction 3 decades ago, the Osprey has been involved in crashes that have resulted in more than 60 fatalities. Most recently, 8 airmen were killed when their CV-22 crashed off the coast of Japan in November 2023, leading to a rare fleet-wide grounding. The primary cause was identified as a catastrophic gearbox failure, exactly the kind of complex mechanical system that eVTOLs aim to eliminate through their distributed electric propulsion. Instead of mechanically complex power transmission, eVTOL rotors have their own electric motors. If one rotor fails, then the others can compensate. But this distributed approach creates new challenges in flight control software, electrical system redundancy, and failure mode analysis. Despite the Osprey's troubled history, the military remains deeply interested in tilt-rotor aviation, but they're actively developing both eVTOL and eSTOL approaches. Both technologies are moving beyond conceptual phases into active testing and operational evaluation, though with different focus areas and timelines. eVTOL companies are securing substantial military contracts and conducting active test flights. Joby Aviation held the largest eVTOL military contract at $163 million through the Air Force's AFWERX Agility Prime program. Most significantly, Joby has already delivered aircraft to Edwards Air Force Base in California, with U.S. Air Force test pilots actively operating these aircraft. Additional aircraft deliveries to MacDill Air Force Base are planned for 2025. Archer Aviation has also been conducting extensive test flights and partnerships with defense contractors like Anduril for military applications of their eVTOL technology. Meanwhile, eSTOL companies like Electra are making concrete progress with defense partnerships focused on immediate operational needs. Electra has secured a $1.9 million Small Business Innovation Research contract from the U.S. Army for powered wind tunnel testing of its hybrid electric aircraft. More significantly, the U.S. Navy has selected Electra to collaborate on contested logistics, the challenging task of transporting military personnel and material from hard-to-reach places or hostile areas. This Navy partnership explores ship-based eSTOL operations, highlighting a key strategic advantage. Electra's aircraft can operate with ground rules of just 150 feet, making it potentially suitable for aircraft carrier operations and forward operating bases with minimal runway infrastructure. Most recently, the military interest has attracted major defense contractor attention. In June 2025, Lockheed Martin Skunk Works signed a memorandum of understanding with Electra to explore opportunities for accelerating development of the EL-9 aircraft, with collaboration areas including digital engineering, manufacturing, supply chain, and business development. Lockheed is an early investor in Electra and will assess opportunities for potential Defense Department programs within the startup. This partnership represents a significant validation of the eSTOL approach. When Lockheed's legendary Advanced Development Division chooses to partner with a startup, it signals significant potential in operational military applications. The military's parallel development of both approaches reveals fascinating strategic considerations. Electra's contested logistics work with the Navy specifically addresses this trade-off. In contested environments, you might not have the luxury of purpose-built vertiports with substantial electrical infrastructure, but you might be able to create or find 150 feet of relatively flat surface. eSTOLs need no runway infrastructure, but require substantial electric power for charging and vertical operations, challenging in austere military environments. eSTOLs, like Electra's design, need minimal runway space and can potentially operate from basic landing strips that can be quickly constructed, repaired, or even improvised from existing surfaces. The FAA's civilian certification standards are typically more conservative than military requirements. This suggests that civilian eVTOLs may need to demonstrate higher reliability and safety margins than their military counterparts. So where does this leave us? Both approaches face challenges, but they're different challenges with different timelines and market implications. Lessons that become clearer when we examine both civilian development and military adoption patterns. eVTOL have attracted substantial investment and media attention. Companies like Joby and Archer are moving through FAA certification processes while simultaneously delivering aircraft for military testing. However, initial civilian operations will likely be limited. Short routes, good weather, premium pricing. The economics presents challenges. Early air taxi services will likely cost several dollars per mile, competitive with premium ground transportation in congested cities, but far from mass market affordability. The early business model will depend on high utilization rates and premium pricing. eSTOL development has been less publicized, but shows substantial commercial interest and concrete military validation. Electra reports significant pre-orders and commitments, plus funded military contracts that demonstrate immediate utility. Civilian orders, however, are largely pre-orders and letters of intent rather than firm purchase agreements. The infrastructure question remains critical for both approaches, but eVTOLs need urban vertiports that largely don't exist yet, while eSTOLs need charging infrastructure at regional airports, potentially easier to implement and already being validated in military contexts. It's likely eVTOLs and eSTOLs will serve different markets rather than directly competing. eVTOLs might excel at medical transport, cargo delivery, urban air taxi services, and military operations requiring vertical flight capabilities. eSTOLs might be better suited for regional passenger services, corporate transport, cargo operations between small cities, and military contested logistics where minimal runway infrastructure is available. Step back, and what we're witnessing is the beginning of electric aviation's transition. This isn't just about new aircraft. It's about fundamentally rethinking how air transportation works. Traditional aviation is built around hub-and-spoke models. Everyone flies through major airports. eVTOLs and eSTOLs both enable more distributed, point-to-point networks. This could democratize air transportation, providing services to communities that conventional airlines can't serve economically. The technology being developed for eSTOLs and eVTOLs will influence all of aviation. Distributed electric propulsion and electric motor technology will eventually find their way into larger aircraft. Companies like Airbus and Boeing are already working on hybrid electric and hydrogen electric concepts for regional airliners. The lessons learned today from eVTOLs and eSTOL programs, including military validation and operational experience, will inform tomorrow's sustainable aviation across all aircraft sizes. At the end of the day, the engineering analysis suggests both approaches have merit, serving different missions and markets. eVTOLs offer the promise of revolutionary air mobility and military vertical flight capabilities, if they can overcome the physics, infrastructure, and regulatory challenges. eSTOLs offer a more evolutionary approach that may have advantages in regulatory approval, infrastructure utilization, and immediate military logistics utility. What's most likely is a gradual rollout starting with niche applications. Medical transport, cargo delivery, military operations, and premium passenger services in specific markets. Mass adoption will depend on solving economic, regulatory, and infrastructure challenges regardless of the technology chosen. The market will ultimately validate which approaches succeed in which applications. Success will be measured not just by technical performance, but by economic viability, regulatory acceptance, public adoption, and operational reliability, demonstrated in both civilian and military contexts. This represents the beginning of aviation's electric future. Whether that future emphasizes vertical flight capabilities or short runway operations, or both, one thing is certain: the engineering challenges being solved today will influence aviation for decades to come. What do you think? Let me know in the comments below. And if you enjoyed this video, don't forget to like and subscribe so you don't miss any future videos. See you next time.